Good morning and welcome to the lecture series on numerical analysis. In the previous chapter 1, we were concerned with the general problem of interpolation. That is, given the set of values as 0, y, 0, x, and y, x and y of x and y to find the polynomial y and x of degree such that yx and ynx agree at the set of tabulated points. It means we were given set of n plus 1 data points are interested to find the polynomial passes to the given data points. So in the present chapter, we shall be concerned with the problems of numerical differentiation and numerical integration. So first, in this chapter, in this lecture, we discuss about the numerical differentiation formulas and their applications. So the outline of the current lecture is as follows. So first section we derive the numerical differentiation formulas. In the second section we show the application of derived formulas. In the third section we derive the maximum and minimum values of the tabulated function. In the last section we will study about the application of the derived figure in the previous section. So how do we find the numerical differentiation formulas? So the general method for deriving the numerical differentiation formula is to differentiate the interpolating polynomial. It means if we are given n plus 1 data points and if we are interested to find the numerical derivative of the given n plus 1 discrete data points, so first we find the interpolating polynomial passes to the given data points, which we have already studied in the previous lectures. So first we find the interpolating polynomial and then we find the derivatives of first order, second order, which is required. So hence the corresponding to each of the formula derived in the chapter 1, we may derive a formula for the derivatives. So for the example, consider Newton's forward difference formula, which is given by this relation number 1, where x equals to x0 plus ps. This is our Newton's forward difference formula, which was used to find the interpolating polynomial near the end start point of the table. Right? So then, now if we differentiate this this equation number 1 with respect to x by using chain rule, then dy by dx equals to dy upon dp, dp upon dx equals to this relation number 2. Now this formula can be used for computing the values of first derivative dy upon dx for non-tabular values of x. It means what? Suppose this is our given data point, this is our x0, this is x1, this is x2, this is xi, this is x1 minus 1 of xn. Now, if we are interested to find the value of the derivative, first derivative, at the point between x0 and x1, it means somewhere here, either some point, suppose x, or between these points. So we use this equation number 2. It means this equation number 2 is used to find the first derivative of non-tabulated values of x. Now, to find the derivative at the tabulated values, we take the simpler form. Put x equals to x0, then we obtain e equals to 0, because our relation is this one, x equals to x0 plus p. If we put x equals to x0, then this gives e equals to 0. So hence equation 2 becomes now dy by dx at x equals to 0, x0 equals to 1 upon x times of this relation. So this gives the first derivative at the point x0, right? Similarly, differentiating the equation number 2, once again we obtain the second derivative. Now this equation number 4 gives the numerical differentiation of second order for the given set of n plus 1 data points at the non-tabulated points. Okay? So at the tabulated point again we put e equals to 0 here, then we get this equation number 5. So this is our second derivative at the tabulated point of the given set of data values. Okay? So in a similar way, different formula can be derived by starting with other interpolation formulas. It means Newton's backward difference formula gives. We know that the Newton's backward difference formula was used to find the interpolating polynomial at the end of the tabular values. Okay? So if we use the same calculation as we did in the previous formula, so dy by dx at x, and it means near about the end point of the data values, which is 1 upon x times of negative of yn plus 1 upon 2 negative 2 yn and so on. So this is our first derivative at near end of the tabulated values. Similarly, this is our second derivative at the point x equals to xn. Similarly, if we are interested to find the derivative at the center points, near about the center point. Right. So we use Stirling formula for this one, and the first derivative at x equals to x0 is given by this relation. Right. Similar equation number 9 gives the second derivative at the center point x equals to x0. Right. Now, the following example illustrates the use of the formula stated above. Means what we have read till now, then application is seen in this example. From the following table of values of x and y, obtain dy by dx and d2y upon dy x squared for x equals to 1.2, x equals to 2.3, and x equals to 1.6. So from here, you could see x equals to 1.2 is the point near about the starting points. Right? 1.6 is the center point and 2.2 is the end point of the data value. And we are finding derivative at the tabulated values only. Right? So we use the tabulated values formula here. So first we write the difference table here. So the first column gives the ordinate values of x. Similarly, y gives the argument values of y. Right? So we are interested to find the derivative x0 equals to 1.2, center point x0 equals to 1.6, and x equals to 2.2. Right? So it means in case of derivative formulas, if given we are interested to find the derivative at the tabulated point, then that tabulated point is considered either x0 if it is in the starting of the table or center of the table, and we consider xn if it is at the end of table. So here 1.2 we consider x0 here, right? So first difference is given by this relation. First difference is nothing but difference between corresponding argument values between 3 minus 2 equals to 1, 7 minus 3 equals to 4, 15 minus 1 equals to 8, and so on. Similarly, second difference is given, forward difference is given by the difference of the corresponding first forward differences, which means 4 minus 1 equals to 3, and so on. Similarly, third forward difference, fourth forward difference, fifth forward difference, and sixth forward difference. Alright, keep here in mind that x0 is our second point in the table. So similarly, the forward difference is first forward difference is the second entry in the column, second forward difference is the second entry in the column, similarly third, fourth, and fifth. Similar. Alright. In case of Newton's backward formula, this is our end point of the tabulated values. So this is our Newton's formula, this is our last position in constructing the formula. Right. So keep in mind this one. It means we select if the point is given tabulated point, then we use formula accordingly. If we use starting point, then we use Newton's forward difference formula. If it is at the center of the value center, then we use Stirling formula. If it is at the end of the value table, then we use Newton's backward formula, and similar formula we use. So here, first case x0 equals to 1.2, so corresponding value is y0 equals to 3, and h equals to 0.2 because given points are equispaced points. So hence equation 3 gives dy by dx at 1.2, which is given by 1 upon x times of this one. So we'll put the required values of del y0, del 2y0, del 3y0, and del 4y0, which are basically these values. This is del y0, this is del 2y0, del 3y0, del 4y0, and del 5y0. Right? If you put these values in this relation and simplify, then we get the first derivative at x equals to 1.2 equals to 18.5. Similarly, equation number 5 gives the second derivative at the point 1.2, and this relation is given by this formula. Now, if you put the required values in this relation and simplify, then we get minus 70.83. This is our first and second. These are our first and second derivative at the point x equals to 1.2. Similarly, this relation second problem was to find the first and second derivative at the end of the tabulated value. Then we use Newton's backward formula, which is given by equation number 6 and equation number 7. So first derivative at 2.2 is given by this relation, and if we simplify, then we get 1 minus 4.53. Similarly, second derivative at 2.2 gives by this relation, and if we simplify, then we get 391.67. Similarly, x0 equals to 1.6 means derivative first and second derivative at the center values of the table. Right? Then we use formula number 8, which is given in terms of Stirling formulas. So first derivative at 1.6 is given by this relation, and if we simplify, then we get 50.13. And equation number 9 gives the second derivative at 1.6, which is given by 104.45. Right? Now, next we define the maximum and minimum values of a tabulated function. It means we are given n plus 1 data point and we are interested to find the maximum value or minimum value of the given tabulated value. Then how do we find this? And we know that maximum and minimum values of a function can be found by equating the first derivative to 0 and solving for the variable. So if we know the one variable function y equals to f, then to find the maximum and minimum value of this function, we put dy by dx equals to 0, then we find the value of x. And at that value of x, we find the second derivative. If it is positive, means greater than 0, then your function attains the minimum value. And if it is negative, then your function attains the maximum value. Right? So same procedure we follow here. So first we find the polynomial passes through the given n plus 1 data points. So to find the polynomial, we use interpolation formulas, which we have already tried. The same procedure can be applied to determine the maximum and minimum of a tabulated function. So for the evaluation purpose, consider Newton's forward difference formula. This formula gives the interpolating polynomial passes through the given n plus 1 data points. Now differentiating this relation with respect to p, we obtain dy upon dt equals to this one. For the maximum and minima, so first derivative must be equals to 0. Hence, terminating the right hand side for simplicity after the third differentiation. It means for the simplification, suppose this relation contains only 3 terms and higher order terms will be neglected. And then if we equate it to 0, we obtain the quadratic for input. Right? So if we put dy by dt equals to 0 in this relation and simplify, then we get this quadratic equation in P. Here, if we compare the coefficients of P square, P1, Pn, and constant terms, then we get C0, C1, and C2. Now, from this equation, we find the value of P, and if we substitute the value of P in this relation, x equals to x0 plus Ps, then we find the value of x, and at that value of x, we find the value of the function, which is either maximum or minimum. Right? So let us consider one example based on this maximum or minimum problem. So from the following table, find x for which y is maximum and find this value of y. So here we use Newton's forward formula. So suppose this is our point x0. So let x0 equals to 1.2, then this formula equation number 11 terminated after second differentiation. Because if we see in the difference table here, these are the values of x, these are the values of y, and these are the forward differences. First forward difference, second forward difference, or third forward difference. Right? So if we substitute the value in the given formula 11, then we get 0 equals to this one, because dy upon dt equals to 0 is 0. Now if we simplify this equation, then we find p equals to 2.8. Now, if we put p equals to 3.8 in this relation, x equals to x0 plus ps, and we know that x0 equals to 1.2. So 1.2 plus 2.8 times 0.1, then x equals to 1.8. It means our point x equals to 1.58 is near about the end of the tabulated values, right? It means 1.58 lies between 1.5 and 1.6. So to find the value of the function at 1.58, we use Newton's backward formula, because this 1.58 lies at the end of the tabulated values. So we use Newton's backward formula here. So Newton's backward formula with xn equals to 1.6 here. Xn equals to 1.6 here. So if you substitute the value of forward differences in the Newton's backward formula and simplify, then we get y at 1.58 equals to 1.0, which is about the maximum value of the function at x equals to 1.58. So thank you for today. In the next lecture, we study about the numerical integration.